coming together, scattering, and making WIMPs, is a cartoon example of something that we use in physics known as a Feynman diagram, invented by the great American physicist Richard Feynman. So this is a cartoon Feynman diagram, so there's a cartoon Feynman. Now, Mr. Feynman will say, well, if this is the diagram, what I can do is reverse the arrows and do other great things with it. And I can reverse all of the arrows in a diagram that describes quarks producing WIMPs would also describe a diagram that describes WIMPs annihilating and producing quarks. So perhaps this is happening now at the center of our galaxy, where there should be a lot of dark matter at the center of our galaxy. Perhaps we will discover heavenly WIMPs, and there are a number of experiments at very many places looking toward the center of our galaxy, trying to find WIMPs. This is an experiment, a balloon that's flying at the South Pole. There are experiments in space. This is Antarctica, not at the South Pole. This is an experiment at the South Pole. These are telescopes in Namibia, and another experiment in space. All these inhospitable places that you don't want to live. This is Arizona. They're looking to the center of the galaxy, trying to see evidence of WIMPs annihilating into quarks. Well, let's ask Mr. Feynman what else we can do. Well, you can reverse some of the signs here, and this diagram can be used to understand the scattering of a WIMP with a quark. If quarks produce WIMPs, WIMPs can interact and scatter with quarks, and quarks appear in nuclei. So a WIMP should scatter with a nucleus, and here around us are WIMPs. So perhaps if we build a sensitive enough detector, it has to be very sensitive because the WIMPs don't interact very much. So this detector has to be put underground, has to be ultra pure, ultra cold, ultra radio pure, ultra expensive, solid, liquid, or gas, and occasionally a WIMP will pass through and just nudge a little bit one of the nuclei. And there are, of course, gazillions of nuclei, so you have to be very careful and look for the scattering, the displacement of one little nuclei. And there are about 20 or so experiments underground throughout the world. This is just some of them, where my colleagues dress up in funny costumes and work underground. They wear helmets in case a WIMP will hit them in the head. And they're looking for WIMPs underground. So this idea that the dark matter is an elementary particle is a scientific theory that we're putting to the test right now. But there's more to the dark side than dark matter. There is dark energy that's causing the universe to accelerate in its expansion. Hubble's law that he discovered in 1929 measured how rapidly the universe is expanding today. Again, you look farther out in space, further back in time, and you can measure how rapidly the universe was expanding at earlier times. If you measure velocity at two different times, you measure acceleration. A change in velocity is acceleration. Now, everyone expected that the universe a billion years ago was expanding more rapidly than it is today, because as the universe expands, gravity works to pull everything back together. But there was a surprise, because astronomers measured that the universe today is expanding more rapidly than it did a billion years ago. The velocity is increasing, the universe is accelerating, and this was such a surprising, fundamental discovery that these three people won the Nobel Prize in 2011 for this discovery. Okay, here's another crazy story. You can't put it on a scale, but nothing weighs something. Empty space has a density, a mass density of 10 to the minus 30 grams per cubic centimeter. Smaller than naive theoretical estimates by a factor of 10 to the 120. A 1 followed by 120 zeros is how much we are wrong. I can't imagine, I've never seen a student's homework exercise that is so wrong as our best job doing this. This weight of space dominates the universe's present mass density. It pulls space apart, causing the expansion of the universe to accelerate, and it will determine the ultimate fate of the universe, and we don't understand it. How can space weigh something? This goes back to the question, was Einstein right after all? In 1917, he proposed the cosmological constant. In 1929, Hubble discovered the expansion of the universe, which was the reason Einstein introduced the cosmological constant, to avoid the expansion of the universe. And eventually Einstein came to realize that the original reason for which he introduced this idea was wrong, and he called the introduction of this constant his biggest blunder, not knowing that 64 years later astronomers would find evidence for it. There's a lesson. Never admit you're wrong. If Einstein had stuck to his original idea, the guy could have been famous. Okay, so I like to think of the cosmological constant as the unbearable lightness of nothing. Observations suggest that there's 10 to the minus 30 grams in every cubic centimeter of space. It's so small, but not zero. I don't like the name cosmological constant. I think it should be called the cosmo-illogical constant. It just doesn't make sense. But how can we get our hands around the idea that nothing can have a mass, that empty space can have a mass? And to motivate this, I'd like to tell you 6 secrets of nothingness. This is the Zen part of this lecture. 6 secrets of nothingness. Okay, we're going to take a little talk about nothing. Nothing is uncertain. Isn't it profound? Nothing is uncertain. Now, uncertainty was introduced in modern physics by Werner Heisenberg, who came up with the uncertainty principle. And so there's a fundamental uncertainty in quantum mechanics. Nothing is uncertain. There's a fundamental uncertainty to nothingness. Nothing is something. Because of the uncertainty principle in quantum mechanics, in the vacuum, in empty space, particles and antiparticles are coming in and out of the vacuum. So I ask my students to close their eyes and think about nothing. Some of them are really good. They've been doing it all quarter. So you can imagine a region of space where there's no matter, a region of space where there's no matter and no energy, zero temperature. You can remove matter, you can pump out all the radiation, but what you can't remove is uncertainty. And this requires that in empty space, at any point in space, particles and antiparticles can come out of the vacuum. So if I look at the universe on very small scales. Look at space on very small scales. It's not empty. There are these particles and antiparticles coming out of the vacuum. Secret number 3 of nothingness: nothing has energy. The particles coming in and out of the vacuum produce an energy density. There's another energy in the vacuum because of the Higgs potential energy. Europe discovered the Higgs boson. At Fermilab, we discovered the Higgs boson. I would have rather the Higgs boson. So what we've discovered because of the Higgs boson is that everywhere around us, there is a potential energy in the vacuum caused by a Higgs potential that's responsible for giving masses to electrons, quarks, and other particles. At every point in space around us, there is a Higgs potential energy of 246 billion electron volts. Secret number 4. Nothing is hidden. My friends who are string theorists, I don't have any friends who are string theorists, actually. But if I did, they would tell me that at every point in space, there are other dimensions of space that are wound up and tightly wound up. That there are really 10 dimensions of space. We only see 3 because the others are wound up really tight. There must be energy associated with these hidden dimensions of space.